Hello there. Today I want to talk about a fun little C# performance surprise that I accidentally ran into, that I knew all of the pieces, but I never put them together in this way. And yeah, I want to tell that story because I think it's actually quite a fun story. So what is the problem? The problem is that I'm working on an old Unity game. Old here means I started writing this in 2016, maybe 2017. It's a game about building machines from blocks. It's called Block Machine because I'm a creative type. And you place these blocks on a grid, and then you can let the execution run, and you can see that these blocks do things, and they move around, for example, down here. And you can let them move around faster, and then they do their thing, and they compute functions. It's basically building computers with a very, very, very obscure kind of language made of blocks. So you have to check whether your machine is doing the right thing to grade it, to figure out is it a working machine. So for this you have to run it against a few inputs. So that's what's happening when I click submit. You can see this takes some time, because this particular machine had to run 86,000 steps. In every step it had to do a lot of updating of blocks and writing them to various places in memory. So I decided to go and profile that. How could I make that faster? And what I found will shock you. The thing that I found is that I spend almost 60% of execution time, or I think rather a little bit more, on a line like this. You have an array of blocks. Blocks are a class type, and you write to that array. Maybe not to index 0, but this is the general setup. Looks like this. You write a block to an array of blocks. And to me, that was surprising. Why would something like this take up 60% of execution time? Let's look at the assembly that is generated by the MonoJIT in release code. It's fairly standard, so you can see you have the C# code here, you have the IL instructions here, and then the assembly instructions interspersed in between. And the one thing that I think you should take a look at is this. There's a call in there. So when we think about C#, I think most people think of reference types, like class types, things that you have a pointer to, and then you pass these pointers around in memory, and then when you write them to an array, that should just be writing that pointer to a place in memory. All of this is, of course, wrong, because C# types aren't necessarily pointers, like the references aren't necessarily pointers. At least that's not the right model for it. And apparently even this writing to memory isn't exactly the right model, because here writing to an array, which should be fairly straightforward, especially when you know the index, for some reason requires a virtual call. You can see that RAX seems to be the place where we load the field into it. Then we look at the vtable here, because the vtable is usually at the first position in the object. And then we index into the vtable to make a call. So it seems that writing to an array takes a virtual call. Curious. Mind you, this is not just for Mono, which is the version of the C# or the C# runtime that Unity is using. This also happens with Core CLR. And this is not a surprise if you know what's happening. It's also not particularly wrong. It's just unintuitive if you don't know that this is happening. So what are we actually doing here? We're calling into this wonderful function. It's the Mono helper that checks when you have a store element, STLM, IL instruction, that things match up. In particular, what I'd like to call your attention to is that we are checking whether the value that we're writing into the array is an instance of the element type of the array. You can immediately see why this would be expensive. Presumably, you have to get some sort of type over here and then make a comparison to another type and also get that type, and then also you have to make this call, so stuff just becomes unnecessarily complex. So at this point, it's at least not a surprise that it's slow anymore. Now we can ask, why do we call that code? And this is where we get into a fun little history lesson. And this is my favorite part of this story. So in 2004, Java 5, Java Standard Edition 5, or otherwise known as Java 1.5, was released, codenamed Tiger. It must have been a really dangerous release, apparently. And this was the first time that Java programmers could write code like this down here, with generic types. It was the Java release that introduced generic types into the language. Now, nowadays we take generic types in languages like Java or C# or whatever other language pretty much for given, but back then that wasn't the case. I guess in functional languages, but in Java-like languages, which, well, in 2004, how many really were there? This wasn't the case. It wasn't just the thing that you expect to have. And it took work from Martin Odersky and friends, who's now better known for Scala, to actually implement this in Java. I think it was mostly a question of how to do it in the runtime, but I'm far from an expert on that particular topic. So, thinking about Java, what for me comes to mind is that Java is this extensive standard library that they ship with, and stuff like checking that two arrays are equal or have equal elements, or that you want to shuffle an array, doesn't seem that far-fetched to need to do generically in such a big library. So what did they do before Java 5? Well, in Java 1 and following, I guess, since 1996, they would write code like this. Because in Java, arrays are covariant. It's not just that they are covariant so they could, that's why they could write this code, but they are covariant so that you can write exactly this code, because there are no generics. What do I mean by covariant? It means, imagine you have an animal class and you have a dog class and a cat class. Dog and cat both derive from animal. Wow, I feel so weird talking all about this object-oriented design stuff. It's not my usual lingo, but let's indulge in it. So when I have an array of animal type, I can store dogs and cats in it, right? Since dog is an animal, covariance means that an animal of dogs is also an array of animals. And I guess you can kind of see, well, that makes sense. If I have a collection of dogs, that's also a collection of animals, but that's not quite right, because an array, you can write to that. And as I told you before, I could write a cat into an array of animals. But if an array of dogs is an array of animals, then I can write a cat into an array of dogs. And that's definitely not right. So generally speaking, when it comes to covariance and generic types in this case, or rather type constructors, so typical ones are like functors in functional languages. The idea is that sometimes this relation holds, so that a subtype means that the array of the subtype is also a subtype of the array of the supertype. That's covariance. Then there's also the other way around, there's contravariance. Both of these are terms that they shamelessly stole from category theory, where functors have similar behavior. But for arrays, neither holds. It's neither the case that an array of animals is an array of dogs, nor that an array of dogs is an array of animals. It just happened to be convenient to pretend that an array of dogs is also an array of animals, because that means that every array is an array of type object. An array of objects, because everything in Java is an object, which means you could write that code. Might not be correct to treat it that way, but yeah, it allows you to write that code. But it means that you have to check whether, when you assign to that array, whether these things match, because otherwise you're getting to that point where you're trying to assign a cat into an array of dogs. So now we get a runtime error for that, and this is what's costing us all of this performance. Now with C#, I thought the story stopped here and said, okay, yeah, C#1 didn't have generic types either, and it only was C#2 that introduced generic types. So clearly they also make the choice of making arrays covariant to be able to write that code. But if you actually look at the .NET framework and in the methods that they ship with it, that's totally not what they do. That's absolutely not what they do. Quite the opposite. They have a lot of functions in their framework, functions that have been there since C#1 when there were no generic types. And these functions, they don't take arrays of objects. They take abstract objects of type array, like literally array. It's called array. It's not an array of objects, it's just a base type array. And every array derives from that base type. So this argument of, well, they want to do the same thing, they had to do the same thing as in Java is clearly not what happened. It's not the same development. Instead, reality is far dumber. Reality is this. This is something that Eric Lippert, one of the godfathers of C# wrote, where they talk about why they have this, why they have covariant arrays in C#. Say, well, obviously this is wrong, but it was added to the CLR because Java requires it. No, Java doesn't run on the CLR, and the CLR designers want to be able to support Java-like languages. Then we added it up to C# because it wasn't the CLR. I can see how at the time it might have been the right choice, but in retrospect, this doesn't strike me like a very strong argument. But okay, mistakes have been made, and now I get to pay for those mistakes 25 years later because my code is now slow. So I want to add a happy end to that story. So this is how I solved the problem. Instead of having an array of blocks, I now have an array of block wrappers. It's a struct. Structs in C# don't have inheritance, so the same problem cannot occur here, because if there's an array of block wrap, it cannot be of a subtype. Functionally, it's doing the same thing, and it immediately made the line completely disappear from the profile. By the way, later I learned that John Skeet did the same thing already in a blog post from 2013. I didn't know. And I guess in C# space, there's little that you can do or say without at some point realizing John Skeet already did that years earlier. So what did we learn today? So I think the first thing that I am reminded of, and it's not a new lesson, but a lesson that I think every time I do it, I realize it was the right thing. Yep, measure. Who would have guessed that this would be the slow part of running a machine? Just writing to that array. It removing that made everything twice as fast. I think even between 2 and 3 times as fast, because it was in multiple places and was only one place with 60%. So it made a huge difference. The second is be curious, because in this case, the original explanation that I had for why C# had covariant ties was obviously wrong when you look at it, and you have to dig deeper. Then stuff that looks cheap in C# maybe isn't. Again, that's not a new lesson for anyone that has worked with C# and trying to figure out what's actually going under the hood. Just don't look at what Mono is doing with structs and how much it moves them around in memory and how bad it is at deleting those copies. And when you're just used to that happening, yeah, just be careful. And finally, of course, reality is generally worse than you imagined. Like this argument of it was there, so we added it. I chuckled. It made me laugh. But no hate on Eric Lippert and friends. I mean, I still think that C# is one of the better languages out there. And yeah, we all make mistakes. Thank you for listening.